Afternoon, good evening, students, and welcome to today's session. So we'll be continuing with heat and thermodynamics. So today we will be moving on to the first law of thermodynamics and its applications. So basically, kinetic theory of gases, what we discussed in the last lecture, and first law of thermodynamics are very interconnected. They are the continuation of the same thing. So you can treat it like part of the same chapter. So most of the applications and numerical problems we'll see will involve both the concepts that we've learned in kinetic theory of gases and the concepts that we're going to learn in first law of thermodynamics today. However, there are certain questions that can be solved by just using the principles of kinetic theory of gases, like the ones we discussed last time, where we are using the ideal gas equation PV equal to nRT, and you're using the relation for RMS speed of a molecule, etc. So we will start by first taking a quick recap of that concept. Okay. So let's take a quick recap of kinetic theory of gases, the derivations that we did from that. We'll just look at the formula again. So we saw that by applying the kinetic model of the ideal gas and the collision theory and Newtonian mechanics to that perfectly elastic collision theory, we got the RMS speed of gas molecules to be square root of 3 times pressure into volume divided by total mass, which can be expressed in either of these two ways: number of moles into molar mass or number of molecules into molecular mass. Okay. Then we saw that by applying the kinetic interpretation of temperature, that is, average kinetic energy is proportional to temperature. We got the relation PV is equal to nRT, or what we can express as capital NKT, where K is the Boltzmann constant, R is the universal gas constant. And then substituting that back here, resubstituting, we got RMS speed also as square root of 3 RT by capital M, molar mass, or 3 KT by small m, molecular mass. Okay. And by resubstituting that, we got that the average translational kinetic energy of a gas molecule is 3 by 2 KT. So this was the last equation that we derived, and this was an important one. So we'll continue with a couple of concepts from here today, and from there on we'll be able to move on to the application of first law of thermodynamics. So hope these equations are all clear to you. Now moving on to something called the law of equipartition of energy. Very important in the derivation of first law, especially later. So law of equipartition of energy. It's basically a continuation of kinetic theory of gases and the concept of degrees of freedom. So from the theory of random motion and Brownian statistic, or the Brownian motion of gas molecules, that is, that the direction of motion for a gas molecule is equally probable along any axis. So we had Vx squares average is equal to Vy squares average is equal to Vz squares average is equal to Vrms square by 3. Okay, this is the relation that we got earlier. If the gas molecules have in general got a 3-dimensional type of velocity, then square the components and average them out. So Vx squares average will be equal to Vy squares average will be equal to Vz squares average because of the equal probabilistic distribution in terms of direction of motion. Equally probable that is moving along the x, y, or z axis or any other axis. Okay. So from that we got this relation here. Now from this we understand something called equipartition of energy. So the equipartition of energy, the principle of equipartition of energy is that the average kinetic energy of gas molecules is equally partitioned or equally distributed over all degrees of freedom. So what is meant by degrees of freedom? Okay. Motion along various axes. Yeah, I'm describing what is meant by degrees of freedom. Okay. So this tells us that half m vrms square is equal to half m vx squares average plus half m vy squares average plus half m vz squares average, because we know that vrms is square root of v squares average, that is square root of vx square plus vy square plus vz squares average. So we square both sides. Okay. This thing's average, which is basically equal to vx squares average plus vy squares average plus vz squares average. So this is still just a statistical definition, that vrms square would be equal to the sum of vx squares average plus vy squares average plus vz squares average. This is coming from this definition of vrms. But now if we include this thing over here, okay, so then we get that half m vx squares average is equal to half m vy squares average plus half m vz squares average, which will become one third of half m vrms square. So this statement now is the equipartition of energy. This is the equipartition of energy over the degrees of freedom. But here, by degrees of freedom, we mean degrees of freedom for translational motion. Okay, we'll discuss about rotational and vibrational motion also. But for translational degrees of motion, the degrees of freedom of, sorry, for translational motion, the degrees of freedom are 3 in number. The degrees of freedom are 3 because of motion along x-axis, y-axis, and z-axis. So you can have motion along 3 mutually perpendicular axes, x, y, and z. So that we say that there are 3 degrees of freedom for translational motion. So now each of those degrees of freedom has an equally partitioned amount of average kinetic energy per molecule. So that is the meaning of the statement of equipartition of energy. Okay. So just note down up to this point. We'll discuss further that next when we substitute the VRMS or half m VRMS square as 3 by 2 kT, this becomes one third of that. So this becomes half kT. Okay, just make a note of this. We'll discuss. We'll note down the last statement also. Don't worry, check it. So just get the gist of this idea that we have written down over here. Okay, so let's understand this concept once more. No, where it said is plus. Let's understand what is meant by this. So whether you have a monoatomic molecule, okay, or you have a diatomic molecule which basically looks like a dumbbell, okay, or you can have any odd kind of shape, can be any kind of shape like this, or a polyatomic molecule. What is meant by translation? Okay. Linear momentum is mass into velocity, and kinetic energy of translation is half mv square. By obviously, where by v mean the center of mass of the molecule. So that is the translational momentum, or what in more common language we call linear momentum. Okay, you might have started rotational mechanics where you have studied about angular momentum also. So there are two types of momenta, angular momentum and linear momentum, like that. Similarly, this is called the translational kinetic energy. Okay, this thing. Now in this, if we take a system of axes, x, y, and z axis, we can divide the velocity of the center of mass into three components: vx I cap plus vy j cap plus vz k cap. So thereby you can see that the kinetic energy of a molecule is like this. The kinetic energy itself is distributed over three translational degrees of freedom: motion along the x-axis, motion along the y-axis, and motion along the z-axis. So therefore, if I look at average kinetic energy, average translational kinetic energy, that should be average of this quantity, half mv squares average. Okay, so that will become half m vx square plus vy square plus vz square. This whole thing's average. So that will become half m vx squares average plus vy squares average plus vz squares average. So this is just the definition of, and over here v squares average is nothing but v RMS square. So that's how we define RMS velocity. We define RMS as root of mean of square. So obviously v RMS square is v squares average. So that's all we are seeing. It's just a definition of a statistical quantity. Okay, a mean, a type of mean which is called the root mean square. But now we will bring in the concept of Brownian motion. Now here, from theory of Brownian motion, each of these are equal. Vx squares average is equal to Vy squares average is equal to Vz squares average, which becomes 1/3 of Vrms square. Okay, so therefore, what we can say is that if we have to separately calculate half m Vx squares average, it would be equal to separately the value of Vy squares average into half m would be equal to half m Vz squares average, and that would be equal to 1/3 of half m Vrms square. Okay, and that would further be from kinetic theory of gases. It would be 1/3 of 3 by 2 kT. Okay, so this we have learned from kinetic theory of gases, that Vrms is square root of 3 PV upon Nm. This is the same thing as 3 PV upon, sorry, 3 RT, or rather 3 KT upon small m. Okay, so just substitute that and you get this here. So this becomes 1 by 2 KT. So this quantity here is equal to this quantity is equal to this quantity. This is called the average translational kinetic energy per degree of freedom. We'll make a short form for this term also later. But as of now, you can see that based on combining all the concepts that we've learned, the definition of VRMS, okay, the specific nature of Brownian motion, and the assumptions of kinetic model, all three things combined, it gives us this result that the average translational kinetic energy per degree of freedom is 1 by 2 kT. Okay, per degree of freedom per molecule, obviously. Talking about, we've averaged it out over the number of molecules because remember, K is R upon Avogadro's number. Small m is capital M upon Avogadro's number. It's molecular mass. And this is molar mass. That kind of thing. Okay. So this is a combination of the concepts that we've been learning since the last lecture. Yeah, I'll give you time to note down the earlier part also. Okay. So this part will seem a little theoretical to you, but you will see that once we are familiar with the basic formulae that we are getting from the derivations, the more important thing will be the application of the formulae in thermodynamics. Okay, so just go with this and make sure you understand the concepts of the derivation. You don't need to memorize it. Yeah, Durgesh, I'll explain. Just note down over here up to this point. Okay. So degree of freedom, I have explained what it means. It means motion along various axes. More the number of axes along which the motion can happen and more the types of motion that can happen, the more will be the degrees of freedom. So when we talk about translational motion alone, there are three possible axes of motion if it's three-dimensional. So it's having a degrees of freedom of 3. Whereas, for example, if I were talking about people in a room walking inside, walking on a floor, okay, they can't fly, so they're walking on a two-dimensional surface. Then such people would have 2 degrees of freedom for their translation. They can either walk, they can walk in a plane where the velocity has two possible components, Vx and Vy, or it can be along two mutually perpendicular axes. So there the degrees of freedom would have been 2. But here gas molecules are moving in three-dimensional space. So they have 3 independent degrees of freedom, motion along the x-axis, y-axis, and z-axis for their translation. Okay, so as you can see in this thing below, it's the repetition of the same concept that we were seeing earlier, that the kinetic energy of a particular molecule can be written in terms of Vx square, Vy square, and Vz square, because that particular molecule has a velocity given by this expression. So then when we are averaging the translational kinetic energy, we are calculating the left-hand side's average quantity. So that becomes the right-hand side's average. So this Vx square's average plus Vy square's average plus Vz square's average, it will become like this accordingly. Scroll up again. But we've already seen that now. The upper part we've already done. Just a minute. I'll scroll up. Achha, the molecular shapes. Yeah, yeah. Okay. 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 Yeah, I'll take it to the last part also. First, just note down up to this part. Finish this part, then I'll take you now. Okay, so this last formula that we have over here, this is the most important formula that we derive out of kinetic theory of gases, that the average kinetic, later we'll convert it to not only translational, but average kinetic energy per degree of freedom per molecule is equal to half kT. So I'll explain what is the difference between translational kinetic energy's average degree per freedom, or in general kinetic energy's average per degree of freedom. I'll explain the difference between that. Okay, so let's understand a little bit more about equipartition of energy and how this applies. So now the general statement of law of equipartition of energy will come something like this, that a gas molecule can, in addition to translational motion, okay, also have rotational motion, okay, and vibrational motion. So there are other types of motion also possible other than translation. Okay. So for example, we have a dumbbell shaped diatomic molecule. It can also be rotating about this axis. It can have this kind of rotational motion also. Okay. Or we have a complex type of molecule which has a lot of different atoms. So the intermolecular bonds are not that, sorry, the interatomic bonds are not that strong. Okay. So this can also be vibrating about. It can also undergo vibration. Even a simple molecule like this, for example, it can undergo vibration. So in addition to translation, they can also have rotational motion and vibrational motion. T is the absolute temperature, beta. ये तो मतलब we are doing thermodynamics for so long now. No? T is absolute temperature. We have discussed earlier also that Vrms was square root of 3 RT by M, which is the same thing as 3 kT by M. So we had already seen that the average kinetic energy was directly proportional to absolute temperature. From that only we got the relation PV equal to nRT now. Okay, so depending on the shape and size of the gas molecule, so gas molecule can have additional types of motion depending on its shape and size. In addition to translation, it can also have rotational and vibrational motion. Now the law of equipartition of energy this states that the kinetic energy of gas molecules is equally distributed over all degrees of freedom. Okay, over all types of motion. So this statement will become clear when I explain with examples. Just note down the statement as of now. So it becomes a more general equation now that the average kinetic energy per molecule per degree of freedom okay, that is equal to 1 by 2 kT. This becomes a mathematical form of the law of equipartition of energy. No, we had written that for translational kinetic energy earlier. Now I'm saying it's general for all types of motion. So it is equally partitioned. So how much is that value equal to? Now it's half kT. Earlier we had written average translational kinetic energy per molecule per degree of freedom. Okay. And when I show you examples, you'll understand what is meant by degrees of freedom for different types of motion. Okay. Just note this down first. It's a molecule, SO2, sulfur dioxide. Take the example of carbon dioxide. This will also have a tendency to vibrate. Okay, so let us understand this in context of some examples. So for example, for the case of a noble gas, monoatomic, example helium. Okay. So it has monoatomic gas molecules. So the shape of the gas molecule is a particle. So monoatomic gas molecules, the shape is a particle, a single atom. No? So you can think of it like a point mass. So if it's a point mass, what about the moment of inertia? We have done moment of inertia in rotation. It's tending to zero. If it's a sphere, okay, you can say it's 2 by 5 mr square or 2 by 3 mr square, depending on whether it's solid or hollow. But if it's just a single particle, then about its own axis, the moment of inertia is zero. So there is no rotational kinetic energy. So therefore, rotational kinetic energy, which is half I omega square, is zero. Okay, and obviously, vibrational kinetic energy is also not there because it's just a single particle. What will it vibrate about? That's also zero. So the only type of kinetic energy this has is the translational kinetic energy, because the rotational and this thing are zero. This. So single molecule of mass m has a kinetic energy like this. So average kinetic energy is half m v RMS square. Okay. The average kinetic energy of monoatomic gas molecules. Okay. This is average kinetic energy per molecule for a monoatomic gas or a noble gas like helium or argon, etc., is given by this expression half m v RMS square. Now we know that translation this has 3 degrees of freedom. Because it's translation in 3 dimensions. Okay. So in that language, we say that small f is equal to 3. So the average kinetic energy per molecule will become 3 times 1 by 2 kT or 3 by 2 kT. Okay. Now, before you note this down, because you're already used to this from kinetic theory of gases, let's understand something contrasting to this. Then we'll come back to this example. Okay. On the other hand, for a diatomic gas, example hydrogen, oxygen, nitrogen, etc. So many diatomic gases. Okay. The shape of the molecule is like a dumbbell shape, where there's actually no rod in between. It's just two particles which are attached by the imaginary rod, which is like the interatomic bond. So if you take the axis of that rod as your x-axis, or the axis of the bond as your x-axis, then you can see that for such a molecule, okay, the molecular mass is 2m. So let's write each atom's mass is m naught. So m is equal to 2m naught. Okay. So for example, for oxygen atom, the molecule, the atomic mass is 16 atomic mass units. So molecular mass of O2 will become 32 atomic mass units. So molar mass of O2 will become 32 grams. Okay. Yeah, so if I'm talking about that, now you can see that it has a moment of inertia about the y-axis. It has a moment of inertia about the z-axis. Okay. Moment of inertia about x-axis is 0 because x-axis is the axis on which both atoms, which you can treat like point masses, lie. Okay, but Iy is not 0. Iz is not 0. So if you think of L like the bond length, okay, and Mo is the molecular mass, sorry, the atomic mass, you can see that basically Iy is equal to Iz is equal to 2 times M into L by 2 whole square, that kind of thing. But how much it is not important for us. What is more important is that they are non-zero. So Iy and Iz are non-zero. Okay. So such a molecule, so such a shape, that is diatomic molecule shape, it's a dumbbell shape, can store kinetic energy by virtue of translation, where its velocity has 3 degrees of freedom, okay, and rotation, okay, but the angular velocity is the sum of angular velocity about the about the y-axis and about the z-axis. Okay. So it can store kinetic energy by virtue of 2 degrees of freedom for rotation and 3 degrees of freedom for translation. Okay. So for such a molecule, the average kinetic energy per molecule will become half I omega squares average plus half m v squares average. Okay. So this will have 2 degrees of freedom and this will have 3 degrees of freedom. So the total degrees of freedom will be 5. Okay. And further, you can write it like this, that rotation about the y-axis, rotation about the z-axis. Whereas translation, you can partition it into 3 degrees of freedom like this. Now, according to law of equipartition of energy, each of these partitions has 1 by 2 kT. So therefore, the average kinetic energy per molecule for diatomic molecule, that will become 1 plus 1 into half kT plus 1 plus 1 plus 1, that is 3 by 2 kT for translation. So this is the proper explanation of degrees of freedom. So this will, in all, it will become 5 by 2 kT. Okay. The average kinetic energy per molecule will become 5 by 2 kT. Okay. So now I'll take you back to the beginning where we understood degrees of freedom for monoatomic gas and then for diatomic gas. So you'll understand what is meant by different degrees of freedom for different types of motion. You don't need to write down everything in so much detail because I'll provide you with the notes. Okay. More important is make sure you understand the concept of degrees of freedom. And you understand the concept of monoatomic gases and diatomic gas molecules. What is the difference in the shape of the molecules and therefore why the degrees of freedom is different for them. Okay, so hope all of you understood the case of the monoatomic gas molecule, why it has only 3 degrees of freedom. Now let's come to diatomic molecules. Okay, so before this we had seen that average kinetic energy per molecule per degree of freedom is half kT as per the law of equipartition of energy. Then we saw that for monoatomic gas molecules, there's only translation possible. So total number of degrees of freedom only becomes 3. Okay. So total only becomes 3 because there is 3 translational, 3 for translation plus 0 for rotation plus 0 for vibration. Okay. But whereas when we came to the case of the diatomic gas molecule, I haven't discussed about vibration. I'll come to that, but for now, just understand that there is no vibration. So the total degrees of freedom is becoming degrees of freedom for translation plus degrees of freedom for rotation, okay, which is 3 plus 2, 5. There is none for vibrational. So additionally, we'll just note down one more point here, that generally diatomic molecules are observed not to vibrate unless at extremely high temperatures. So that's why we have taken the vibrational degrees of freedom as 0. Okay, so let's understand a quick numerical application of these type of concepts. So next we have two containers having some kind of ideal gases each. Okay. So this has container A has helium gas at pressure of 2 atmospheres, volume of 5 liters, and temperature of 300 Kelvin. Gas or chamber 2 has oxygen gas at a pressure of 1 atmosphere, volume let's take same 5 liters, and a temperature of 200 Kelvin. So first of all, find the ratio of VRMS for molecules in chambers A and B. The first set of question is going to be about ratios. So next we have to find the ratio of average kinetic energy per molecule in chambers A and B. And then we have to find the total kinetic energy of gas molecules in chamber A and the total kinetic energy of gas molecules in chamber B. For this part, you can take the value of R as 8.31 joules per mole Kelvin. You can take 1 atmosphere as 10 raised power 5 pascals. So just try this question out, people. Okay, so let me check out the answers that you people have sent. Uh, Durgesh, okay. So it's all about basically applying the correct formula. Okay. So when we are talking about RMS speed, remember RMS speed you can write in terms of either this, but then you need to know the total number of molecules, or you can write it as this, which is easier. Okay. So for the first part, VRMS for chamber A is to VRMS for chamber B. You can just use this is square root of TA by TB into mass of B, which is basically oxygen, and molar mass of A, which is helium. Okay. So temperatures, if I remember, were what were the temperatures now? 300 and 200, I think. Yeah, 300 and 200 should be B. Okay. And helium and this thing. Okay. So 3 by 2. Now molar mass of oxygen is 32 grams and molar mass of helium is 4 grams. So this should become 2 root 3. Okay. Whereas when we come to the average kinetic energy per molecule, we should remember that law of equipartition of energy. Average kinetic energy per molecule per degree of freedom, that is half kT. Okay, so that means average kinetic energy per molecule is equal to F into half kT. Okay. Now in chamber A, we have helium. Okay, so degrees of freedom is 3, monoatomic. Okay, and the temperature is 300 Kelvin. So this average kinetic energy per molecule in chamber A is 3 into 1 by 2 K into 300. Similarly, in chamber B now, we have oxygen. So degrees of freedom is 5, diatomic, and it's at temperature of 200 Kelvin. So this will tell us that the average kinetic energy per molecule for the gas in chamber B will be 5 times half kT. So this much. Okay. So the ratio will just become 9 by 10, isn't it? You just go through this and verify what you have done, whether it agrees with the answer properly or not. It's just about selection of the correct formula or the most convenient formula. Okay. So this is the important thing. Average kinetic energy per molecule per degree of freedom is this, and the fact that F is equal to 5 for diatomic. Degrees of freedom total is 5 for diatomic, and degrees of freedom is total 3 for monoatomic. Okay, now so hope this part is clear to all of you. Now let's move on to the next thing. We have to find the total kinetic energy of gas molecules in chamber A. Now this is something we'll have to develop the formula for, okay, but it will come from the concepts you've seen before. So third case, in chamber A, we have helium at pressure equal to 2 atmospheres, volume equal to, it was 5 liters, and temperature equal to 300 Kelvin. Right? This is what we had. Just verify once. Yeah. All right. So now we know that the average kinetic energy per molecule, we just now saw this, that was equal to 3 into half kT. Okay. So total kinetic energy of molecules, this will become what? The number of molecules multiplied by average kinetic energy per molecule. Okay. So that is number of molecules into 3 by 2 kT over here, because degrees of freedom was 3 for monoatomic gas. Okay, so this you already seen before, so I'm not, it's helium gas. Now let's take this further. So it becomes 3 by 2 NKT. Okay. Now N is nothing but number of moles into Avogadro's number. So therefore NK is number of moles into Avogadro's number into K. So that is nothing but small nr. Okay. So remember here, this is number of molecules. Okay. Whereas small n is number of moles. So there's that relation between them. Okay. So therefore, this thing, the total kinetic energy is nothing but 3 by 2 nRT, which we can also write as 3 by 2 PV, because PV is equal to nRT. So you can see it is 3 by 2 times the pressure, which was 2 atmospheres. So 2 into 10 raised power 5 pascals into volume, which was 5 liters. So 5 into 10 raised power minus 3 meter cube, because 1 liter is equal to 1000 milliliter, which is 1000 cubic centimeter, which is, okay, 10 raised power minus 3. We had done this in a numerical last time also. So you should remember this conversion, that 1 liter is equivalent to 1000th of a meter cube. So 5 liters becomes this. So this becomes very simple. So Pascal into meter cube will give us joules. So 3 into 5, 15 into 10 raised power 2. So 1500 joules. 1500 joules is the total kinetic energy of gas molecules in the chamber E. So you can see with minimum amount of extra work in the calculation, nowhere I've tried to calculate the number of moles using PV equal to nRT. I've just substituted wherever RT was required, or nRT was required, I've replaced it with P into V. So this is one clever way of doing the calculation, that especially for these kind of questions. So you'll get used to this method of calculation as we do more questions. So you will find that in this chapter or this section, heat and thermodynamics, there aren't so many tricks and constraint relations and twisted things in the questions. The questions are all very conceptual. So as long as you're clear with the concepts in the basics, and you're clear how the concepts convert into formulae, VRMS, average kinetic energy per molecule per degree of freedom, from that the total kinetic energy, etc. As long as you're clear with those concepts, you will find it very easy to solve the questions in comparison to mechanics. Okay, and you can score a better sort of percentage of marks in attempt versus marks scored. You can get a better percentage in heat and thermodynamics at the JEE level. Of course, the weightage is less compared to mechanics. Mechanics has a weightage of nearly 35%. heat and thermodynamics has a weightage of only about 15 to 20%. But if you are clear with the concepts and you practiced enough questions, you can score 100% of the questions that come from heat and thermo, whereas that is little difficult to do for mechanics. So it's a very good way to bolster your overall score at JEE, whether you're talking about mains or advanced level. Heat and thermodynamics is one of those topics where you can boost your scoring. Now just use this same method to calculate the fourth part, the total kinetic energy of molecules in the or the gas sample in the chamber B. So in B we had oxygen at pressure of 1 atmosphere. The volume was 5 liters only. The temperature was 200 Kelvin. So what is the total kinetic energy? Yes, very good, Samarth and Devansh. Okay. Yeah, Shikhar, let's see the answer. Yes, Durgesh, that's correct. Very good. So here remember oxygen. So the degrees of freedom will become how much? 5. So F is equal to 5. So average kinetic energy per molecule is 5 by 2 kT. So total kinetic energy will become number of molecules into 5 by 2 kT. So that is 5 by 2 nRT. So 5 by 2 PV. That will be the formula over here. So the pressure remember is 1 atmosphere. So 1 into 10 raised by 5 Pascal into the volume is 5 liters. So 5 into 10 raised by minus 3 meter cube. So 25 by 2 into 10 raised by 2. So that's 1250 joules. This will be the total kinetic energy of gas molecules. Okay, so hope all the parts in this question are clear to you. If there's any doubt, please let me know. So you can see that we've almost utilized all the concepts and formulas that we have discussed for kinetic theory of gases so far. And that's all there is as far as this chapter is concerned for application. You have to just know how to apply these formulae in different type of applications. At the same time, conceptually, you should also know how the formula is come. So assumptions of the kinetic model, the collision theory concept that we are applying, the Brownian motion concept that we are applying, equipartition of energy. These are all things which you should be conceptually 100% clear with. You don't need to memorize the statements of all that, but you should be clear with the concepts, and then you should know the formula inside out. Okay, so let's look at another example question. But actually before that, we will see that since according to kinetic theory of gases, or you can say according to the assumptions of the kinetic model of an ideal gas, okay, gas molecules do not have any intermolecular attractive forces. Therefore, gas molecules store energy only in the form of their kinetic energy. Okay. So therefore, the internal energy of a gas it is nothing but the total kinetic energy of its molecules. Okay. So internal energy is given by the formula U, and this becomes number of molecules into degrees of freedom into 1 by 2 kT. It becomes the product of number of molecules into the degrees of freedom into average kinetic energy per molecule per degree of freedom. So internal energy becomes this, where of course capital N is small and number of moles into Avogadro's number, and Avogadro's number into Boltzmann constant is R. So the internal energy is also given by this formula. Okay. So this is actually, you can see the first idea for our next section, which will be laws of thermodynamics. This is the first of the three terms that we have in first law of thermodynamics: internal energy, work done, and heat. So the first term is the internal energy of the gas. So internal energy is nothing but the total kinetic energy of its molecules. So that is degrees of freedom by 2 into nRT. Yeah, I'm coming to that. For polyatomic gases, Durgesh, I'm coming to that. It depends on the shape and size of the molecule. It can be 6 and upwards of 6 also. Whereas there are certain polyatomic gases which can also have degrees of freedom 5. If the molecule is linear in shape and does not have vibration, then it can also be 5. But yes, polyatomic gas molecules can have 6, 7, and 8 degrees of freedom also. So hence there is no direct formula for it, the degrees of freedom. It depends on the gas we are talking about, and also the temperature range in which we are discussing about the gas. So the two standard values for degrees of freedom will be for monoatomic 3 and for diatomic 5. Of course, for diatomic at extremely high temperatures, it will become 6 because there will be one vibrational degree of freedom also. But generally speaking, for diatomic gas molecules, F is equal to 5. So in our physics numerical problems, these are the two standard values of degrees of freedom we take. F equal to 3 for monoatomic and F equal to 5 for diatomic. Triatomic is a type of polyatomic only, so it comes in the general case of polyatomic. So I'll come to that section. We'll write down a note about that. Just make sure you're clear up to this formula first. So triatomic molecules can be linear in shape, they can be non-linear in shape. Like we saw the example of carbon dioxide. It's a linear molecule, so it more or less behaves like a diatomic molecule. But then it also has vibration at nominally high temperature, not extremely high temperature. Even at nominally high temperature, it can have vibration. So for polyatomic molecules, for more than 2 atoms per molecule, the concept of degrees of freedom becomes a little bit more tricky. And it also depends on each type of molecule and each type of temperature range in which we're talking about the molecules. So we cannot give one definite answer that it has to be 6 or it has to be 7 or it has to be 5. It depends on various other factors. So hope that is clear, Durgesh and Samarth. Yeah, you will be learning about degrees of freedom in chemistry also in thermodynamics, and there you learn a little bit more in detail about polyatomic molecules. But for physics, actually, the two standard cases of monoatomic and triatomic are okay. You just need to remember those. So F is equal to 3 for monoatomic gases. F is equal to 5 for diatomic gases. Okay. Unless at extremely high temperatures. Okay. Resulting in vibration. Okay. Degrees of freedom cannot be predicted for polyatomic molecules. Depending on shape and size. The translational degrees of freedom will always be 3, but the rotational degrees of freedom can be upwards of 2. So basically they can be 2 or 3, depending on whether it's a linear molecule or a rigid body shaped molecule. And the vibrational degrees of freedom similarly can be upwards of 1. I mean, can be 0, 1, 2, etc. They can have different axes about which they're vibrating. Rotational degrees of freedom, you can say generally speaking, is either 2 or 3. So total degrees of freedom can be 5, 6, 7, etc. So if you get a numerical problem with a polyatomic molecule, the degrees of freedom will be given to you. You won't be expected to know it beforehand. Whereas diatomic and monoatomic gases, you have to understand the standard case. They are like this. Okay, so now we come to the final part of today's theory discussion, which is the statement of the first law of thermodynamics itself. So the first law of thermodynamics deals with a thermodynamic process. So for a thermodynamic process, So this is any process where the state of a gas undergoes some change by the exchange of heat, okay, and or mechanical work with it. Okay. See what we mean by state of a gas is defined by pressure, volume, temperature, and the interrelation between them, PV equal to nRT, which is the ideal gas equation, is also called the equation of state. Yeah, so on the zeroth law we've already seen in calorimetry. We have done the application of zeroth law. So basically, the zeroth law says that if one body is in equilibrium with another one, then there is no heat exchange between them. Okay. So if body A is in equilibrium with body B and B is in equilibrium with C, then A also must be in equilibrium with C. So when are they in equilibrium? When their temperatures are same. Whereas when do they exchange heat? When they are at different temperatures. So that's all about zeroth law. You don't need to really know anything separately about zeroth law. It's more about the law of calorimetry. That is, in any heat exchange, the heat lost by the body which is cooling down will be equal to the heat absorbed by the body or material which is heating up till they achieve equilibrium. That is, their temperature becomes common. So anyway, now coming back to this, the first law of thermodynamics tells that for any thermodynamic process, Q is equal to delta U plus W. Okay, where Q is the heat supplied to the gas. You must remember this. This is not the heat absorbed from the gas, but it is the heat supplied to the gas. Okay. So Q can be positive when actually we are supplying some heat, and Q will become negative when we are absorbing some heat from the gas. Delta U, as you might have seen, guessed, it is the change in internal energy of the gas. And that is why I said that we've already done one part of first law, because we've understood the formula for internal energy. So delta U is the change in internal energy of the gas. Okay. And now equally important, W is the work done by the gas. You must remember, W is not the work done on the gas, it is the work done by the gas. Okay. So we'll also discuss in which case these quantities are positive, in which case these quantities are negative. But this is the statement of first law. The heat supplied to the gas equals to the change in internal energy plus the work done by the gas. Okay, so sorry, what we mean by this is that it is a process in which, or you can say it's a process for which the state of the gas undergoes some change. So its pressure, volume, and temperature, at least one of them is undergoing some change. Such a process is called a thermodynamical process. And that's happening with the exchange of heat and mechanical work and or. Okay. So when we understand examples of this will become more clear. So for example, if you have having gas in a cylinder like this with a piston, and you're pushing the piston down with some force. So as a result of that, what is happening? Work is done on the gas. Okay. Now, as a result of this, the gas will tend to heat up. Now, if, for example, the walls of the gas chamber are made of conducting material like metallic, then heat might come out. But if they are made of insulating material like they're double walled vacuum walls, so heat will not escape out, then Q will be zero. But work done on the gas will be converted into internal energy. Whereas if you are doing work on the gas but allowing heat to come out, so Q will also be negative, W will also be negative because heat supplied to the gas is negative. Heat is being withdrawn from it. Okay. Similarly, if I have a situation where now I have a gas in the cylinder with a piston and now I supply some heat to it. Okay. Now if I fix the piston, I don't allow it to move, then the work done is zero because the force that the gas is applying on the piston is not doing any work. But the heat I'm supplying will get converted to internal energy. So I'll see the internal energy increases. On the other hand, if I let the piston be free, it might displace in this direction. So the force that the gas is applying on the piston, that force would be doing work. So in this case, W would be positive. I'm supplying heat to the gas, so that would be positive. And internal energy will tend to increase or decrease. That depends on how we are doing the process. Whereas here, work is done on the gas. So W in our definition will be negative because W is the work done by the gas. So if the external agent is doing work on the gas, then the work done by the gas will become negative. If heat is getting absorbed from the gas, is going from inside to outside, that means Q will be negative because we are absorbing heat from the gas. The external environment is absorbing heat, the gas is losing heat. So that's how each of these quantities can be positive or negative. And internal energy, we've just understood by the kinetic theory of gases earlier, that it depends on the state of the gas, the pressure, volume, number of moles, temperature, etc. How it depends on those. We have already seen one formula. So next time onwards, we'll start looking at applications of this. Okay. Now there are a few extra things in kinetic theory of gases which you will see in your module, like Maxwell's distribution curve. Okay. The concept of mean speed as opposed to RMS velocity. Okay. And also the concept of most probable speed or most probable velocity. So these are some things that we will discuss in addition to. Okay. So these are some more extra things in kinetic theory of gases. So they are just one of things that we need to discuss in the future lecture. But you will not really be getting numerical problems based on this. The conceptual part of kinetic theory of gases, which you require for problem solving, is what we have discussed up till now. Okay. And then in H.C. Verma, there are few extra things in the kinetic theory of gases chapter. Like there is the concept of humidity. Okay. There is vapor pressure, etc. So you can read them for your general knowledge, but that's not required for us in our syllabus. These things are not required. So apart from what we've learned in kinetic theory of gases, the extra few things which we'll pick up in the next few lectures will be Maxwell's distribution curve, most probable speed and mean speed. And of course, we'll carry on with first law of thermodynamics from here. So that's it for today's session, people. Wish you all the best. Yes, I will send you a list of questions to do from the module as well as H.C. Verma. Okay. you'll see that this chapter is like this, that once you're clear with the concepts, the questions are not going to be difficult to solve. They are going to be more or less application of formula type of questions. You just need to be sure about what formula to apply where, for which the conceptual ability is the most important thing. Okay. So that's it for today, people. Wish you all the best.